10.3 notes, apply properties of chords. So a quick reminder from our first section in the definition of a chord. The definition of a chord here is a segment with endpoints on the circle. So remember, there can be all kinds of chords within one circle and they can be different lengths. But we're going to be talking a lot today about congruent chords and how we can know if they're congruent, or if they're congruent, what property that leads to. So notice we have no vocab to start with today, though I am going to squeeze a couple in on our last page of notes. And we're going to jump right into our theorems today. So theorem 10.3 says, in the same circle or in congruent circles, and I will tell you, typically we keep it in the same circle, but we just need equal size circles if we're talking about them. Two minor arcs, and remember a minor arc is less than 180, are congruent if and only if their corresponding chords are congruent. So over here in my picture, I see that chord AB and chord CD are congruent. So if those are congruent, then the arcs that go to them, this arc AB and this arc CD, are also going to be congruent. So filling out our blanks here, arc AB is congruent to arc CD if and only if segment AB or chord AB is congruent to chord CD. So if I have congruent arcs, I have congruent chords. But I'm going to turn this right around, because if I have congruent chords, I also have congruent arcs. So this argument can go back and forth either direction. So if you're given one of the two, then the other one has to be true. So if you have congruent arcs, you have congruent chords. Or if you have congruent chords, you have congruent arcs. And remember, that is necessary that it's either in the same circle or on the same size circle. So moving on right now to example 1. Notice right now I have two different circles, but right away I notice that I have a congruent mark on both radii, which means circle A and circle D are congruent, which they tell me in my directions as well. They also tell me and mark that chord BC and chord EF are congruent. So if I have congruent chords, I should have congruent arcs. Well, over here on arc EF, it's 125 degrees. They want me to find arc BC over here. Because segment BC and segment EF are congruent chords, that lets me write this, in congruent circles, going to be lazy here, then the corresponding minor arcs BC and EF are also going to be congruent. So if this one's 125, this one's 125. I know that was a lot of writing for such a simple answer, but I want to make sure you understand the concept as well. So moving on to the bottom of the page, we have two new theorems down here. All right, the first theorem says if one chord is a perpendicular bisector of another chord. So you'll notice here that SQ in this circle is perpendicular and bisects this chord TR. Then the first chord that is doing the perpendicular and the bisecting is going to be a diameter. So QS here is perpendicular and it bisects TR. That means that QS or SQ, however you want to call it, because it doesn't matter, is going to be a diameter of the circle. And our next theorem just kind of flips this around, kind of the converse. If a diameter of a circle is perpendicular to a chord, then that diameter is also going to bisect the chord. So that means that segment FH is congruent to HD, however you want to name it. They told us that. And then if we have congruent chord parts, we're also going to have congruent arcs. So arc FG over here is going to be congruent to arc GD down here. So diameter that is perpendicular bisects the chord, and then because the chord has congruent parts, then there's arcs that are congruent as well. And I should be careful. These should be curved. These are arcs. All right, first page of notes done. Let's move on to page 2. And I'm going to tell you right now, I got lazy and didn't replace it. I don't care for this problem up here, so we're just going to skip it. So let's go right to the bottom of the page of this notes. Shorten up these notes here. All right. I'm going to use this diagram of circle E to find the length of segment BD. It is super important as you read through your homework and such, always look to see, am I finding a segment or am I finding an arc? Because we want to make sure we're finding the same thing. So when I look at BD, it's definitely a segment. Looking at the picture, I can see AC is the diameter because it's going right through that center point E there. And it's a diameter, and it looks like it's also perpendicular to BD. So we know from our last rule that if it's a diameter and it's perpendicular, it's going to also cut that chord right in half or bisect it. So AC is going to bisect BD, cut it right in half. So BF is going to equal the same thing as FD. And we notice that FD down here is 6, so that means BF is also 6. So if I want the whole thing, I'm going to take 2 times my 6, and I'm going to get 12 for the whole length. When I get that full thing there for BD, that full thing will be 12. And if you want to fill this out, BD is going to be twice what FD is here. All right, next theorem, and one that's going to come in handy a lot. In the same circle, or in congruent circles, 2 chords are congruent if and only if they are equidistant from the center. So we know from way back in chapter 3 that if you want the shortest distance between a point and a line, it needs to be perpendicular. So you'll notice E to G here is perpendicular. You'll notice E to F here is perpendicular. That means it's finding the shortest distance from the center out to the chord. Well, if those are equal distance inside, then my chords are also equal distance. So if my chord, this AB here, is congruent to CD here, those are congruent, then they have to be equal distance to the center. So E to F will be equal to E to G here as well. And I'm going to just be a little bit picky. I'm going to erase my line up here because it does have an equal sign, so that means that I'm actually looking at the length of EF is equal to the length of EG. So just like on page 1, I want to kind of stress, if you have congruent chords, then they have to be equidistant to the center. What's a chance I can write this big word here? Equidistant to the center. But I want to stress too, if your chords are equidistant to the center, they're going to be congruent chords. So once again, this theorem can go back and forth. You can have congruent chords, which will make an equal distance to the center. Or you can have equal distance to the center, which will make congruent chords. So moving on to page 3. On page 3, we see that we have a circle F, and it tells us AB is equal to CD, and they're both 12. Oops, off on that line. So AB down here is equal to DC here, and they're both 12. That means my chords are congruent. If my chords are congruent, they have to be equal distance to the center. So we know that these are going to be equidistant from the center. So this and this will be exactly the same length here. EF down here on the bottom will be equal to this FG up here. So my 3x on the bottom is equal to my 7x minus 8. And I'm ready to solve for x. They definitely didn't leave me a lot of room here. I'm actually going to move my 7x to the other side to get my x's together. So 3x minus 7x will give me negative 4x equals negative 8. Wow, hope you can read my writing. And divide by negative 4, and x equals 2. So when x equals 2, they're equal distance. Let's plug it in. It tells me to find EF. So I plug in for 3 times my 2. And that gives me 6. I don't know why I didn't write them in that spot it gives me. But just as a quick check up here, let's check this one. What's 7 times 2 minus 8? Well, that's 14 minus 8. And that's also 6. So you'll notice I get that equal distance on both sides. So when x equals 2, I'm equal distance to the center. All right, number 1 here. If the measure of arc TV over here is 121, they want me to find the measure of arc RS over here. So quick reminder, I'm in one circle, so I don't have to look for equal circles. And I notice that I have congruent chords because both SR over here is 6 and TV here is 6. If I have congruent chords, I have to have congruent arcs. And if my arc TV was 121, then that means that the measure of arc RS has to be the exact same. So this is also going to be 121. Congruent arcs make, congruent chords make congruent arcs. Tongue twisted up here tonight. All right, number 2. It says find the measure of arc CB, the measure of arc BE, and the measure of arc CE. So let's look at the picture and see what we can figure out. I notice that point A here, the center of the circle, has a chord going through it. A chord that goes through the center is definitely a diameter, and that diameter is perpendicular to the other chord. Well, from our earlier rule, if our diameter is perpendicular to a chord, it will also bisect the chord. So that means that that chord CE is bisected. And if the chord is bisected, it's also going to split this arc in equal parts. Technically, I probably shouldn't be putting those congruent marks on those arcs, but I'll do it here just to kind of keep us on track. And since you can't see what I'm pointing to, it helps if I can make a mark on there. So that means that arc BC is exactly the same as arc, and I'll put the measure of that, BE, because we split it exactly in half when we split that chord in half. So that means that 4x over there is going to equal our 80 minus x. Add an x to both sides. I get 5x equals 80. Divide by 5 and x equals 16. Which is great, but it didn't ask me for x. It asked me for the measures of some arcs. So let's go ahead and find some measures. So the first one is the measure of CB. I look up here at CB, it's 4 times my x, so 4 times 16. It looks like that's going to be 64 degrees. Next one, it asks me for the measure of BE. Well, BE is 80 minus my 16. 80 minus 16 is also 64 degrees, which is good because those arcs should be exactly equal. And it asked me for one more arc, arc CE. And arc CE is the full arc, so I'm just going to add my 64 plus 64, and I'm going to get 128 on that arc. That's a plus sign in there. All right. Last example on this page, but don't worry, I've got one for you on the next page too. It says here that in the diagram in example 4, so I'm going back to the top of the page. I'm just going to do a quick sketch, kind of see where we're at. I have AB as one of my chords. I have DC as a chord. Center of my circle was F, and F went perpendicular to this one at G. And F went perpendicular to this one at E. All right, I think I have the important pieces of information. All right, let's label up what we know. It says in this new diagram, using this picture from example 4, AB is 27. So my chord AB is 27. Then it says EF is equal to GF, so both of these are equal at 7. And it says find the length from C to D. Well, I want to kind of note a rule so we know how to explain this later. It looks like I'm equidistant to the center because these are both equal distant from the center. There's my equidistant from the center. So that should make congruent chords. So if AB equals 27, CD should also equal 27. So they should be the same. All right. I want to add a couple things the book didn't add to this, so let's go one more page. You'll notice I'm going to start at the top here with some definitions. I did warn you at the beginning of the notes I was going to grab some. I do want to tell you these 3 definitions, they don't necessarily need to be part of 10.3, but I did want to get them in there at some point. These are kind of words that might show up, especially on a standardized test, and I'm going to kind of throw them in here just so we start getting used to some of these words. These are very much geometric terms that could come up in any time in any class. So I just do want to make sure we know these. All right, I will tell you, pictures mean a lot here, but I'm going to add some words on here as well, and I hope I have enough room to write these words in my nice handwriting with this stylus. Okay, first one, concentric circles. You might think of them more as something that looks like this. Here's a center, here's a circle. I'm going to run out of space. Here's a circle. It's not letting me draw. Here's a circle. Okay, you kind of see where this is going. It looks kind of like a target if I could draw with any part of accuracy. These are circles with the same, that share the same center. But have different I'm going to write this two ways here. They have different size radii. Basically, it just means different sizes. Okay, so we have a small circle, medium circle, big circle. We could keep going. We could have 50 circles that are concentric as long as they share the same center and they keep going out from there. Those are concentric circles. All right. This is why I should probably type these all up instead of trying to write these. All right, next word is circumscribed circle. Now, some points I really want to stress on this vocab word. Okay, first thing, I see this prefix circum. Okay, one of the vocab words you might remember from any math class is a circumference. And the circumference goes around the outside of the circle. Well, something that is circumscribed goes around the outside. Now, it's important to notice that this time I have a circumscribed circle. That means my circle, this circle, is going around something else. So I have this circle on the outside, and then I might have a shape on the inside, okay? So my circle, because that's what comes after circumscribed, so my circle is drawn around, there's kind of like my circumference, around a polygon. So you're going to have a shape inside. Now here's one thing I do want to stress too. On my polygon, all my vertices, those are my corner points, are on the circle. Okay, so you'll notice on this pentagon, 1, 2, 3, 4, 5, all of them should touch the circle, the edge of the circle. So this vocab word, circumscribed, describes whatever shape comes behind it. So the circle is circumscribed around the polygon. So the circle is the one on the outside. Okay, so let's use the same idea on our next vocab word, where this is an inscribed circle. So now it's still talking about the circle, but now this circle is inscribed. All right, once again, what's the chance I can draw this at all? Here's my circle, and here's my shape that goes around, okay? So this time my circle is inside, because that's the shape I'm talking about, is the circle. So my circle is inside a polygon. And all my sides of my polygon, they're tangent to the circle. So it's kind of important to know with these vocab words, it doesn't mean just draw a triangle or something and draw a circle inside. That's not an inscribed circle. The circle actually has to touch every side of that polygon. So you'll notice the circle touches this side once, and this side once. So there's those tangent lines that are going around the outside of the circle. Okay? So inscribed circle or circumscribed circle, they have to touch all the sides or all the vertices of the shape that's it's going around it or is inside of it, either way. Okay, 3 vocab words. I'm going to be honest, you're not going to use them in your homework tonight, but I did need to squeeze them somewhere in your notes before we start taking a quiz on some of our material. So these are kind of a side note, but I do want to make sure you have them. All right, let's do our final problem here for the 10.3 notes. All right, again, one of my favorite ones. And just a quick hint, guys, when I add these problems to the notes, that's a pretty guaranteed idea. You're probably going to see them on a quiz or test. So make sure you go through these problems, check them out, and make sure you know how to do them. All right, so the question says, find the radius of the circle. Well, if this is my center right here, this definitely looks like my radius right here. I'm trying to find the value of that radius. All right, not a lot to go with here. But let me give you some ideas from some concepts we had today and some rules that you can use when you're working with these circles. Okay, one is this segment that has this 6 on it. If I extended this segment, okay, I'm going to kind of make it dash because it's not really in there, but I do want you to look at that. If I extend that segment, that's a diameter, okay? Now, they only gave me part of the diameter from here to here, but if I extended it, it is the diameter. And it's perpendicular to that chord that has the 16 on it. Well, my concept from this chapter or this section says if my diameter is perpendicular to a chord, it's going to bisect the chord. It's going to cut that chord in half. That means my 16 can be split into an 8 and an 8, bisect exactly in half. All right, so we use something from this chapter, but I still want to find x. Well, x is the radius of my circle, and you're drawn this way. Is that the only radius of the circle? No. You're allowed to move that radius anywhere you want in a circle because every radius in a circle is exactly the same length. So I'm going to choose to draw this radius from the center to this spot on my circle. And I'm allowed to do that. And what I now see is I have this triangle that I know this length is 8, this length is 6, and I'm looking for x. And yes, I know my picture is not very much to scale, but that's pretty standard for my geometry class. All right, a right triangle missing one side. Good thing we know Mr. Pythagoras, little a squared, b squared, c squared coming at us. Which one is our c? Well, it's the one across from the right angle, so that looks like that's going to be my x. And I'm going to plug in my legs of 6 and 8. Remember, those two can interchange. It doesn't matter which one's in which spot. 6 squared, 36. 8 squared, 64. When I add 36 and 64, I get 100. And for once, I gave you a pretty number. Square root of x squared, and I get 10. There is the radius of my circle. And just so you know, and I'll give you this heads up right now, the 2 of these you have on your homework will not get you a pretty number. You're going to decimal, but don't be afraid. Just follow the same process and you'll be okay. All right, once again, just like earlier, I will not have you do book work here. I do want to kind of just focus you and keep it a little bit easier, and I realize some of you might not have your books either. So I have a 10.3 worksheet. You will be assigned here on Google Classroom. So please try your best at it. Email me some questions if you're not sure of something, and we'll go from here. And just to give you a quick heads up, we're going to take a break from notes now, and after 10.3 this week, we're going to do a quiz review on Wednesday, and we will be looking at a quiz on Friday on 10.1 through 10.3. So make sure you know where all your notes are, all your examples, all your homework, and start gathering those together, because after you finish this homework, you will be taking a quiz this week. So make sure if you have questions, you email me, send me a message, and we can clarify those questions. Thanks for listening.